So page 27 in OneNote, we've got an elevator. Oh, Ms. Earhart, we've never done an elevator problem before. Okay, that's okay. Just focus on the physics, right? And so, yeah, long story short, you may see prompts either on our exams or the May exam that you've never seen before. One year, the May exam had speed bumps on a ramp. And even the teachers looking at it, we're like, I didn't teach speed bumps. It was, they were testing, can you handle think about what's happening with speed bumps on a ramp, okay? And so it's just adapting and focusing on the physics. Now you've ridden an elevator, hopefully, so you know a little bit what's going on. An elevator is on the 20th floor of a 40-floor building. So we're starting midway. At time equals 0, in other words, when the timer begins, the elevator is at rest. Aren't they so nice? Maybe tomorrow, by the time they get to the 20th floor, maybe it's in motion, right? Maybe it didn't stop at the 20th. So the infamous tomorrow, might it have an initial velocity? Sure, it's not always at rest, but here it is today. And the doors have just finished closing. In other words, we're about to take off. The student is on the elevator and they have a smartphone with an app that can measure vertical acceleration. And true story, those are really out there, okay? The student takes data for 10 seconds, starting when the timer began, t equals 0. By the way, you'll never calculate with an equation with t equals 0. If you find yourself plugging in 0 for time, reread it. It's when the timer begins, okay? The acceleration is shown on the right. Let positive values represent up. So they are defining the positive direction, and thankfully it agrees with standard sign convention. And so up is positive. And notice on our acceleration time graph, you've got quadrant 1 and negative values. And always read your axes. Don't assume, oh, it's a velocity graph. Yesterday it was a velocity graph, today it's a velocity graph. No, read your axes, okay? And if you're looking at it, you're like, what are all those dots? So real life is not just a straight line, right? It's a collection of data points that you do a trend line for. So overall, if you look at the dots from 0 to 2 seconds, what can you collectively say about the trend line from 0 to 2 seconds? Don't connect the dots. What would the trend line for 0 to 2 seconds look like? Straight horizontal line, right? So 0 to 2, you got 0 acceleration, right? 2 to 4, again, the dots dance around, but overall, you have what going on from 2 to 4 seconds? Two to 4? What's happening overall? Isn't it basically your trend line is at the positive 3 meters per second squared? And so don't get bogged down by the individual dots. Look at overall data trend, okay? And so similar thing, 4 to 6, 6 to 8, 8 to 10. And if you're like, what? The lines aren't connected. Straight up and down, you can do. So there is our acceleration time graph, trend line basically, okay? And so when you see a graph, always think 3 things. You can read it. What does reading an acceleration graph really tell us? Do you remember? Acceleration is not our velocity. It's a change in velocity. And how do you get a change? Remember, acceleration happens because of a force, some push or pull. And so it's telling you when you read this acceleration graph, it tells you who's pulling you, okay? So you can read a graph. Who remembers the other 2 graphical strategies for any graph? The S word, slope. What does the slope of a acceleration time graph give us? jerk, which we don't do, okay? And so not in AP1, just FYI. So we won't be doing the slope. You would just say if it's constant or not constant. But the other strategy we will use, what's the other strategy? An A word, what is that? Area. What does the area of an acceleration time graph tell us? What physics does it give us? Change in velocity. And don't forget the delta. It's not going to give us any old velocity, not average, not initial, not final. Technically, it gives you a change, which, if you kept that going, is equal to a final minus initial. Yes? Okay, so any graph, those three things are your go-to tools, okay? I haven't even read question 1. It says, qualitatively and quantitatively describe the motion of the elevator at the following times, at 5 and 10 seconds. Now, you can't just look at 5 seconds because if you think too quick, oh, at 5 seconds, 0 acceleration, it must be stopped. That's not the right answer. You can't just look at an acceleration graph and know immediately what's happening. And so before we do that, let's tell the whole story, because today they ask 5 and 10. What if tomorrow they ask 3 and 7? Are we ready to answer at any time? And before I do that, what does qualitative and quantitative mean? Like what? How it appears. So description, words, right? And so what if we just did numbers on this whole thing? Do you think AP is going to give us full points for not doing any kind of qualitative appreciation? No. So at the end of the day, y'all, you got to do what they ask. And so if they say give descriptions and numbers, you want to give them both. And by the way, I don't remember where points go for all these little things that are going to get graded. At the end of the day, just, give them what they want. So before I look at 5 and 10, let's walk through the story of this graph. It all begins with something not on the graph. You can't know anything about the object if you don't know what the beginning of the story is. So today, the beginning of the story, when that timer begins, the initial velocity is what? 0. Now, how do we know that? They said it starts from rest. Now, I'm about to put a velocity reading on an acceleration graph just because it's going to be part of the progression. And so at t equals 0, they told us the initial velocity is 0. Now look, 0 to 1 second, 0 to 2 seconds. How is this acceleration going to change that motion? Is it? If you read it, there's no pull. Remember, acceleration tells you who's pulling you. So from 0 to 2 seconds, there's no pull, no force, no area, no change in velocity. What's my velocity at the end of 2 seconds? If nobody pulls on me and I started at rest, still 0. So the velocity at 2 seconds, still 0. Not very interesting yet. And then 2 to 4, notice we've got a positive acceleration. So we're getting pulled to the positive, up, right? However, it is an elevator, so they're pulling up. What's that going to do to my object who starts at rest? What's the story if you're pulled up? Or take this approach. Earlier, we talked about area. Remember, it's from your data line to the axis. So I'm not going all the way down. I stop at the x-axis, right? What does a positive area, a positive change in velocity tell us? My velocity that starts at 0 is going to have a positive change. So my final velocity would be positive. I move in what direction? Positive. That should make sense, right? Because the sign of your velocity should be the sign you're going. If I start at rest and you get pulled to the positive, you should speed up in the positive direction. And so we're going to speed up in the positive direction. Now we can do some numbers along the way. Area, base times height, 2 seconds by positive 3. What's our delta V for that 2 to 4 seconds? Base times height, 2 times 3. And everybody hopefully says 6. And so I know that my change in velocity is going to be a positive 6. So what's the final velocity at the end of that time? The velocity at 4 seconds would be positive 6. Everybody with me? And then 4 to 6. What happens 4 to 6? When you read the graph, who's pulling you? Nobody. No pull, but that does not mean you're not moving. It means you have no change in velocity. No change in velocity. So what's the velocity at 6 seconds? It's still 6 meters per second. In other words, the elevator for 2 seconds is going to coast at a constant velocity, right? 0 acceleration could be for an object at rest, but it can also be when you have no change in velocity. Is everybody good with that? Let's keep it going. What about 6 to 8? Who's pulling on us now? We've got a negative pull. We've got a negative area. Remember, we were moving in the positive direction. We sped up and then we had a positive constant velocity. But now something's pulling us back. What's happening to our object now? We're slowing down. So now we're slowing down. Elevators slow down, thank goodness, right? They don't just come to an immediate stop. I mean, that's still a slowdown, but you know, you're not jumping out of a moving elevator. It's not Hollywood. They slow down. What direction am I going? Look at symmetry. It's our friend when we have it. What do you mean nowhere? So we're slowing down. What direction are we traveling during 6 to 8? Not at the end. I get what you're saying now. Still up. Still moving in the positive direction. Okay, it's not till symmetry occurs that our change in positive 6 and our change in is a negative 6. Do they cancel out? And what's our velocity at 8 seconds? 0. So we return to rest. And then 8 to 10, who pulls on us? 8 to 10 seconds, nobody pulls on us. We return to rest. What's our object going to do? It's going to stay at rest. Everybody equals 0. So the velocity at 10 seconds is going to equal the velocity at 8, which we came to a rest. Does this make sense? The progression? Okay. Now, will you always have symmetry? No, but when you see symmetry, let it help you, okay? And so let's answer the question. Quantitative, qualitative, 5 seconds. What's true about the object, which is an elevator today? What do we say at 5 seconds? Right, it's moving in the upward direction, positive direction, at a constant velocity. Quantitatively, we know it's at 6 meters per second. And so that's what I'm going to come right on the first part. And so elevator, object, if you said object, that's totally fine, okay? Just don't say the dog. If you say the dog when it's an elevator or car, that can be a little confusing. So either keep it generic object or be specific with elevator. And here's another tip, don't say it. Some problems have more than one object. So if you just go it, are you talking about the red ball or blue ball, right? So elevator is moving upwards, or you can just say positive direction at a constant velocity of 6 meters per second. And if you hadn't shown any work, you would then show your base times height, right? Okay, you can even say area from, what was it, 2 to 4? Was a change in velocity equal to positive 6. You can kind of, what we did verbally and up there in our graph, you could restate. And so change in velocity, final minus initial. If ever in doubt, show the greater. More physics, okay? They care about the physics. Prove your knowledge of physics. Good on 5 seconds. What about 10 seconds? What's the story? Qualitative, quantitative. What's the story of your object? Ten seconds was the end. What do we say by the end? We came back to rest at 8 seconds and there was no acceleration and no change. So at 10 seconds, it remained at rest. And so elevator came to a rest at 8 seconds and with no acceleration, remained at rest. At 10 seconds. So V at 10 seconds equals 0. Good deal there. Now, if you just wrote it equaled 0, would you still get point? I mean, again, I haven't seen the rubric in a while, so you can check the rubric later, but that's probably collectively, probably worth 2 or 3 points. Okay, if there's 2 or 3 physics things to think about, it's probably worth 2 or 3 points. They're grading physics. Okay, at t equals 10 seconds, is the elevator above, below, or at its initial position? Remember, it started on the 20th floor. It went through those different accelerations. Where's the elevator now? Don't think we've talked about it. You can't just look at an acceleration graph and know position. You got to think about the story. So is the elevator at the end of 10 seconds above, below, or did it return to its initial position? What say you? Above, why? Okay, so we had a positive area. We sped up in the positive. We went constant velocity. in the positive same direction, right? And then we slowed down, but we were still going in the positive direction. And then we came to a stop. Did we ever go back down? Not in this graph, right? Maybe if we had 10 to 20 seconds available, maybe it went back down, right? But it only went up. And so it is above the initial position. Make sure you answer their question. And it says, explain your reasoning, always be ready to justify, okay? If you leave the answer right here and don't explain, you probably get no points, okay? No points. And so it's above the initial position. You can say the elevator increased velocity in the positive direction. I'm going to abbreviate some to keep it all in. Then when a constant velocity in the positive direction. By the way, what I'm doing here, I wouldn't abbreviate every single word on the AP exam. Okay, I'm just running out of space. Okay, so we increased velocity in the positive direction. We went constant velocity in the positive direction, and then we slowed down in the positive direction. And so, moral of the story, we never went downward. Okay, what would it take? What if they asked an extension? What would it take to move in the downward direction? What would you want to see on the graph? What would the graph need to look like for the object to go in the negative direction? Well, how do you know what direction you're going? What do you have to look at? Sign of position, velocity, or acceleration. What tells us the direction we're going? The sign of velocity. And so we would want to keep going. We need a negative velocity. Well, how do you get velocity from an acceleration graph? Area. You would want to see more negative area. If, 11 to 12, 10 to 12 seconds showed another negative acceleration, well, we returned to rest and then we went more negative, right? And so, or if 6 to 8 happened over more time, right? If that -3 acceleration happened for more seconds, it would come to a split second stop and then it would come back in the negative. Maybe it doesn't let anyone off at the top, right? There's a glitch. I don't know. Good deal on B, what it would take to come back down. All right. Then we have some empty blank grid lines. On the grid below, draw graphs representing the velocity and the height or vertical position. If it makes you feel better to make it an X, go for it. As functions of time only during the 10-second interval. Assume the initial height of the elevator is YO. And notice it's already there on the graph. That's the only thing on the vertical axis even labeled, right? Velocity 0, but on the position, your 0 mark is down here. You think you're going to get full points if you start it at 0 on the position graph? Probably not. So make sure you read and play the game, right? Pay attention to detail. Be sure that the graphs have proper shapes. They mean a curve is a curve, a straight line is a straight line, and then slopes during appropriate times. Now notice both graphs do have the x-axis time labeled. Do you think they're grading that for accuracy? Yeah, the time parts they're grading for accuracy, but the vertical axis, I mean, there's a couple things there they're looking at, but overall, they're not grading the vertical axis beyond those 2 points. And so you can do either one of them first. We'll just go in order, velocity. And so we already spent time with velocity In the first 2 seconds, what do we know about the velocity of the elevator? It's 0, right? And so we're going to come down here for 2 seconds. You have 0 velocity. So you start at 0 and you end the 2-second interval at 0 and you just connect it straight away. Please don't not put a mark thinking the AP grader is going to be like, oh, if I don't mark it, they'll assume I know what I'm doing. Okay. If you don't darken in the 0, you don't get that point. There's some kind of point associated with it. You won't get that. All right, what about 2 to 4? What do we know about 2 to 4 seconds? You started at 0. What's the final velocity of that second interval? 6 meters per second. Positive, right? So they're testing, do we know to go in the positive side? Now, we don't have numbers, so you don't, maybe just go midway, right? So leave a little room just in case. If it makes you feel better, you can put a 6 there. You don't have to. It's not going to be graded, that part. How do I connect those lines? Because that is going to be graded. Do I want a straight line to connect, or do I want a curved line to connect? Why curved? Okay, now careful, you had a constant acceleration, right? So what does constant acceleration look like on a velocity graph? How do you get the acceleration from a velocity graph? Do you remember that? Slope. So if I have a constant acceleration, I want a constant slope. So actually on this one, you want a straight line. The position one will be curved. There it is. So we'll get one of each. But on a velocity graph, you want a constant positive acceleration. And how do you get acceleration? It's the slope of a velocity graph. Okay, what about 4 to 6? What's the story, 4 to 6? There's no acceleration, so we don't want any changes in velocity. What are we going to draw on the velocity graph? Straight horizontal line for a constant reading, right? 6 to 8 seconds, we had that negative acceleration. We said it was going to slow us down, and the symmetry told us we'll return to what velocity at the end of 8 seconds? 0. How do I connect those two? Straight line or curved line? Straight with a negative slope, right? It's our only option there, but we want a constant negative acceleration. And to get that on a velocity graph, you want a constant negative slope. And then 8 to 10 seconds, we do what? Boring. We stay at rest, right? Okay. What about position? They told us, hopefully you caught on, we got to start it at Y0. If you go back to the very first sentence, they said you start on the 20th floor. What if tomorrow they're on the 0th floor, right? Then you'll go to the 0. But we start here. Now, here's where I would say, oh, a student who draws this in pen is going to regret it, because there's a lot of different motions here. I would do this one in pencil. OneNote allows you to erase, but if you're using paper, use pencil. AP exam, they really like blue or black ink, but physics is one of the exams where you can use pencil, and it's for graphical purposes. And so, you know, you sketch it in pencil, and when you love it, you're like, yes, I'm not changing my answer. Trace over it in pen, okay? So we start at the YO position. First interval, 0 to 2 seconds. What are we going to do? How's our position changing? How is your position changing in the first 2 seconds? It's not changing. And so we're going to remain at YO. Who remembers how you get position or change in position from a velocity graph? Area. So there's no area in that 0 to 2 seconds. And so no change in position. We keep what we had. And then we've got 2 to 4. We're going to speed up in the positive direction. We've got a constant velocity in the positive. We've got a slowdown in the positive direction. Y'all, careful in the next few places, because do we ever come back down? We already answered this in part B. We don't ever. So we're not ever going to be here in the negative. Now, don't scratch yours out, but don't think you're going to return to the 0th floor. You're not even returning to the 20th. And so maybe the last position you have is right up here. Now, don't connect any points yet. In 2 to 4, maybe we only go up this much. 4 to 6, maybe we go up this much. And then 8 to 10, maybe we go up this much. Don't play connect the dots. I just want you to know you got to leave room. If I did something like, oh, I got to go all the way up to the top here, there's no more room to go. Do I want to go off the grid line? No, you want to stay on the grid line, okay? Now, how do I connect each interval? So 2 to 4 seconds, we are accelerating. My velocity is changing. And don't forget, the slope of a velocity, of a position graph tells you velocity. And so how do I show a slope increasing on a position graph? Curve up or curve down? Level off, not level off. Swoop up. And so it's just maybe going to be gradual here. And please don't be the student who says, oh, I'm going to draw the line that kind of looks curved and kind of looks straight. Maybe they'll give me credit, right? If the grader can't clearly tell the intent, you don't get the point. So if you draw in pen and you're like, oh, that could be interpreted as straight, do this. Tell your grader. Say, grader, this is a curve. And you'll get the point. Okay? What about 4 to 6? How do you show constant velocity on a position time graph? Constant slope or diagonal, right? And so, hey, grader, this is straight. Maybe I forgot my ruler and I did the best I could, but grader, this is straight. Maybe I spell it out. There we go. What about 6 to 8? We said we're slowing down in the positive direction. How do I show a slowdown on a position graph here? Do I want to swoop up again? I want to level off. And so wherever I ended, show a level off. It's another curve, right? And it looks like my points need adjusting. What's true, 8 to 10? No more change in position. So it should be a straight line, horizontal straight line, right? Yes. Everybody good on that one? And again, if you want to see how the NMSI graders allotted points, you can pull up the key and kind of see where it all goes. It's not going to be every single data point, every single line. A lot of times they'll do a collective, okay? All right. Questions on that one? All right. Let's move on to page 31. So we're going to try the paragraph one together. Again, 2 and 3, if you want to try them. I definitely think you should try. Make note to self. Try page 30, okay? It's just a qualitative, quantitative type of problem. Okay, there's some calculation, there's some graph drawing, there's some students arguing, And so that's a good quantitative, qualitative. Do you understand the physics going on? Do you understand the math going on? If you get, super revved up for physics, you can try F2, but we're easing into the lab base. So there's not going to be lab base on the next exam like this one. Okay, F4. A model rocket initially at rest, at ground level, is launched upwards starting at time equals 0. So when the timer begins, it launches up. The rocket has an upward acceleration as long as the engine is firing. But once the engine stops firing, the rocket is in free fall. By the way, AP problems usually don't say, once the rocket engine stops firing, it's in free fall. They'll just say something like, and it quits firing at 5 seconds or something. And you have to know that if the engine's not firing, it's in free fall until it reaches the ground again. So this is going to be a ground to ground. It's going to go up, straight up, by the way. That's the next sentence. It's purely vertical. Real rockets, even model rockets, they go off to the side, right? Air and everything else, trajectories. This one's just going to go straight up, come straight back down. One dimension kinematics. The graph to the right shows the velocity of the rocket as a function of time, where positive values are up velocity. And then it tells us the graph is not drawn to scale, which means that T1 and T2 and T3 that are marked on the horizontal axis are not necessarily equally spaced apart. And so it's tricky, even for myself sometimes. You start looking at a graph for 5 minutes and you start saying, oh, those look equal. And you forget that they told you they weren't. And so a lot of graphs aren't drawn to scale. AP does a nice job about telling you when something's not drawn to scale, but don't convince yourself otherwise later. And so explain what the rocket is doing when the timer reads T2, whatever that time is. When the timer reads T2 seconds, what's happening to the rocket? Well, let's go back to the beginning. What's the story here for our little rocket? Again, the diagonal, I think that's a safe, okay, yes, diagonal, that's a safe, true statement. But T1, T2 to T3, don't start convincing yourself times are equal. But what's happening to our rocket? 0 to T1, what's happening? What's the story? It's speeding up in what direction? In the positive. So we get a positive velocity reading, right? So it's speeding up in the positive direction. And if it starts from rest, it has a positive acceleration on it, right? Thank you, engine. And you can also look at the slope there. It's got a positive slope. It's got a positive acceleration. Now, does that mean gravity's not working on it? No. Okay, gravity is working on it, but the engine wins, or you can look at it as you're being told basically something about the net acceleration. Good deal? All right, part 2, again, don't look at, timing equivalence or anything. Just because T1 to T2 looks bigger than 0 to T1 doesn't automatically make it true. But what's happening in the second part of the story? Why is it going to start slowing down? It's now in free fall. How do you know that? Oh, they told us. Pretend they didn't tell us. What's evidence that it's in free fall at this point? The engine provided an upward acceleration, a positive slope. Now we have a negative slope. Is the engine on? No. So it's actually at T1 that the engine stops. Now that doesn't mean our object stops, right? Notice we reach some kind of maximum velocity. I'm going to go in and call that V1. I learned from last class to start giving some labels. So the maximum speed velocity at the end of T1, I'm going to call V1. And so now we're in free fall. It's going to start slowing down. And notice at T2, it crosses that axis again. We come back to a velocity of 0. Does that mean we're on the ground? Where is the rocket? It's at the peak. And so part of our answer, and I'll restate it over there, the rocket is at the peak, or you can call it a max height. And it comes to a split-second stop. If you want to call that V2, I guess you can. But it comes to a split-second stop, and then what happens? Notice I still have a constant slope, T2 to T3. What's the story of T2 to T3? It's coming down. And so now the rocket is coming down from the max height or from the peak. Okay, it's still in free fall. And notice it's going to reach another Vmax, which I'm going to call V3, right? So it's going to reach another Vmax, but now in the negative direction, because we're in the quadrant 4 of the velocity graph. Everybody good there? Okay. Explain what the rocket is doing at T2 seconds. So we already answered this one. We said the rocket is at a semisecond, I don't know what, that's my word, semisecond stop, or a small stop, or instantaneous stop at the peak or max height. Okay. And it's in free fall. Rocket is in free fall. Here's what you don't get points for. Here's kind of, you know, the misconception trap. Oh, it comes to a stop, so acceleration is 0. Acceleration is not 0 at the top of the peak, okay? Everyone good there? So an explanation, I didn't emphasize it, but yes, you can use numbers to support or equations to support, but make sure you have at least one sentence on a justify your reasoning or explanation. That is not the paragraph response. And so B says, which is greater? And they're going to talk about speeds and times, and notice the check boxes. So you're not going to get points for check boxes. It's all for part 3. Explain your previous 2 answers. And by the way, don't conflict yourself. Don't check, you know, greatest upward speed, and then later on in your paragraph say greatest downward speed. If there's a conflict, you're going to lose a point, okay? So explain your previous 2 answers in a well-reasoned, and focus on the physics, stay on topic, organized, hopefully it flows in sequential thought, paragraph. And so paragraph, at least, I know that we talk about data, you know, you want sufficient, and I still agree with that. But having graded a paragraph response before, they are looking for at least 3 sentences, okay? I always end up writing more because typically there's like 5 things to grade. So I look at it as, you know, 3 to 5, quality over quantity, but you probably can't do it in one. Cite appropriate physical principles. Y'all, that's equations and laws. Later on, we'll talk about Newton's laws, conservation laws. And so those are the principles that it's talking about. And it says use the graph shown above or construct one of your own. Now, I'm going to be honest. If you go look at the rubric for this one, I disagree with the philosophy that they implement. And here's why. You remember up above where they said graph not drawn to scale? meaning the T2 to T3 and T1 to T2 are not necessarily equally spaced and such, they're going to use area to solve the problem. But to do area, you got to look at the base. You have to make assumptions about the bases of those triangles. And they told us it's not drawn to scale. So I think they have conflict within themselves. So I'm going to answer this not with area. I'm going to answer it with physics principles. We'll get the same answer, but I disagree with them saying don't draw, this graph is not to scale, and then they start using it like it is to scale. Does that make sense? Okay, to me, they conflict with themselves. And so I'm going to forget the check boxes. What do we need to answer? We need to answer the greatest upward speed or the greatest downward speeds, or are they equal, but more important, why? And so we're going to look at V maxes. And so V max in either direction is what we're going to look at. And then also the time up. How does it compare to time down? Okay. And so using principles, I'm going to draw a sketch. Let me come over here. Let me draw the rocket. Now, not necessarily really the rocket, but here's my ground. Here's my rocket, whatever. So rocket. And it's going to fire up, right? Initially, it starts from rest. And the first part, we've got the engine, phase one, right? Engine has a positive acceleration, and it's going to speed you up to a V max. And I called that V1, I believe. And so V1 is my V max in the upward direction. And at that point, what happens? The engine turns off and the rocket becomes what? An object in free fall. And so in free fall, now the object is going to start slowing down. So here we're in free fall, and it's going to have a negative acceleration. Now, by the way, did they tell us that the engine had like 5 times the acceleration of free fall of gravity? We don't know if this is a weak engine or a strong engine, but we know direction, right? Engine gives a positive acceleration, but free fall has that negative acceleration due to gravity. And when it reaches the max height, what do we know? Split second, 0, right? And this is at T2. So if you want to call that V2, okay, it's going to be 0. And what happens next? What goes up must come down, right? Gravity's still working on it. Gravity doesn't stop. And so that max height, I'm just going to shift over so that I don't clutter my picture too much. We're going to start at that rest. And remember, gravity is symmetrical. So notice that I have this section looking symmetric, right? That's on purpose. Gravity doesn't care if you speed up or slow down. Remember the simulation I did last time with the dots? Okay. But here's the thing, the engine doesn't turn back on. The whole thing's not symmetrical. What's going to happen after this? Gravity is going to keep speeding it up, right? And so that V3 that we have when you return to the ground happens down here. And no, it's not 0. We don't care about the velocity after it hits the ground. We care about it the last moment it's in free fall, and that's right before it hits the ground, okay? So this is going to be our V max in the down direction. And hopefully, walking through that step by step, do we know the first answer? I haven't directly given it away. It's not equal. The Vmax on the way up and the Vmax on the way down. Look at the location. What if I add one more thing? Remember that symmetry I was talking about? That symmetry, I return to V1, but this time I'm going in the negative direction. So gravity from that, end of engine up to the max height, it slows the rocket down from what I've called V1 to 0. And then that first part of the down goes from 0 back to V1. But now it's just moving in the negative. What happens after that? It keeps speeding up, right? And so V3, if you will, is going to be greater than that V1. And this is Vmax in the downward direction is greater than Vmax in the upward direction. Does that make sense? Now we got to check a box and explain that part in words. Okay, we'll do that and then come back to time. And so, let me hold it right there. Make sure you understand the diagram, what's going on. I broke it up into pieces. Okay. On the way up, 2 pieces. Technically on the way down, I broke it up into 2 pieces. Okay, so here goes our paragraph. So which is greater, the greatest upward speed reached by the rocket or the greatest downward speed? And we said it's going to be the greatest downward speed, and we need to explain why. So if you draw the picture and you show enough physics, the principles, you can talk about how the V1 equaling whatever that V1 equivalence on the other side. So what did we say? The velocity is a maximum right before it hits the ground. In other words, Vmax down is greater than Vmax up because as it falls down from the max height or peak at the same position as Vmax up, the rocket has a negative V equal to Vmax up. And here, not that, don't just go symmetry, because give some explanation. But for you and I's terms, we've been looking at that symmetry of free fall. And so that equivalence. Then the rocket falls more. Or you can say accelerates, continues to accelerate. To the ground. Therefore, Vmax in the down at the ground is greater than that Vmax up. And with the picture, I did the picture, came to conclusions that way too. Does that make sense? I'll pause right there and then we'll do time. Now for time. And so here's where, if you look at the rubric, they're going to start talking about bases of triangles. And I say, wait a second, you said it wasn't drawn to scale. And so if it's not drawn to scale, you can't do that. Okay. And so let's come up with another way. So let's use our equations. And they didn't really tell us about the acceleration of the engine compared to that of gravity. So I want to try and not, get into acceleration terms, but looking at time up as it compares to time down, if it was in free fall the whole time, it would be equal, right? If it was just gravity the whole time, ground to ground, time up equals time down. But it's not. But so they are not equal. There's your first point, because you have the engine. The question is the engine going to be more or less time? Well, we got some speeds we can work with, some velocities. I do want to point out something is equal though. Rocket, engine or not, what is equal on the way up and on the way down? Think scalar. Distance. And so from the ground to max height and max height back to the ground, distance up does equal distance down. And that's actually going to be essential to answering the problem, the way I'm going to approach it. So again, without using area, without using acceleration, but we know acceleration's happening, this little distance up, and I guess we can write it this way, the whole distance up is equal to the whole distance down, right? But even just the little bitty up is equal to the little bitty down. So that part is going to be equal in time because they're both in free fall right there, looking at the highlighted blue. And so this little bit time up is equal to the little bit time down. So really it's a question of, well, what about when the engine's on compared to when it's in free fall for the rest? Okay. Now, you can't just say, oh, distance is the same, acceleration is not that, you can't just say the one with greater acceleration has less time, because that would be assuming the initial velocities are the same for those two sections, but they're not. Notice the velocity here is equal to that negative V max up. But on the way up with the engine, it was equal to 0. And so using our defining equation that involves time, displacement, and our velocities, okay, we know both are going to be a constant acceleration. So y'all remember this equation? Or if you take it out, y'all remember that? Hopefully it looks familiar. It's rearranged a little different. So this is that fourth equation that you can use for objects with constant acceleration, but it's not on the formula chart because it's based on defining equations. And so we know delta x is the same. So delta x, we're just looking at the down and up pieces, not the top. But here we know that that distance is the same. But let's see, who has more time? Well, it would be the one with the smaller average velocity, right? So more time would be the smaller average velocity. And so on the way up, if we look at initial velocity was 0 plus V max up, whatever it is, right? And then the displacement down would equal initial, but wait, that's not 0. That was equal to a negative V max up, same magnitude though, plus you'll have a negative of some number bigger. So if you want to make up some numbers, that would be a bigger value than the other. Now the signs mean they're still going to add, right? And there's the time. And so 0 plus a big number divided by 2. And then the down direction has two velocities, neither are equal to 0, they would be summing together, and it would be greater than what you get on the way up. Does that make sense? If you want to play with some numbers, maybe it goes up to 100. And so this would be 100 as well, but then you're going to speed up even more. And so which one's going to take more time? Is it on the way up or on the way down? What do you think? 100 divided by 2, 50 times some time, right? We know the distances have to be equal for those little chunks. And then I have 300 over 2, that's 150 times time. So the one with the greater time will have the smallest average velocity. Who's got the smallest velocity? Engine or the gravity portion? Engine. And so the engine has a smaller average velocity, so it'll have a greater time. And collectively, how are we going to check the box? Well, put it together with the little up and little down there at the peak. We're going to have more time on the way down than we do up. Does that make sense? Kind of, sort of? Okay. And so over here, time moving, they want which one's greater. I think I said greater. Greater would be the whole time downward. No. What'd I say? More time would be with the engine. And so time moving upward, let's go explain it. And then we'll be done here. And so the time going upward, again, the key talks about area, and I just think that's mean because they said graph not drawn to scale. You can't do area without it drawn to scale. Time going upward includes the engine and a little free fall time. And then maybe I start a new sentence. The little free fall time is symmetrical or equal time with the little free fall downward time. I wish now I had said section A, section B, section C, section D, so I could give TA, TB, TC, TD. So note to self, we could have done that. The little free fall down time. And how we know that, it returns to the same position. Therefore, using delta x equals VI plus VF over 2, all times time, the time with the engine is greater than time in free fall to the ground, because the average velocity with the engine is less than the average velocity in free fall. And then if I had showed, I showed my math up above, so I'd either direct the greater with an arrow, or you can rewrite it down there, but we had done that right here. Does that kind of make sense, spirit of it all? Paragraph response. So the grading, by the way, do you still get full points if you do it some way, a little bit different than what you see on, the rubric? I mean, as long as it's correct, yes. You can't do it an incorrect way and get full points. So we didn't have time to go back to page 19, but if you can, I did record it. It's on Canvas. The ones there at the bottom deal with variables, okay? The exam coming up isn't heavy on variables. There might be some, but it's a very big AP principle that we got to get familiar with, all right? All right, y'all have a great Monday. Wednesday is our exam number 3.